All right, ladies and gentlemen, welcome back to section 4.2, day 1. Today we're going to talk about the mean value theorem. And we're going to jump right in here, taking a look at this red curve here, which I've gone ahead and labeled f of x. And what we're going to do here is we're going to pick 2 points on this curve. Now, it doesn't really matter which 2 points they are. So I've picked point A, which is somewhere around, x equals negative 2.5. And so if A is going to be my x value, then I were to plug A into the function, then f of A would be the y coordinate. And same thing with point B, which is somewhere around 2.25 it looks like. And same thing, if I plug that into the function, the y coordinate is f of b. So here's what I can do with these 2 points. We're going to go back to chapter 2, actually, where we talked about the idea of the average rate of change, which is represented by the slope of the line that connects these 2 points, which is going to look like this, maybe? Let's see if I can get that. Let's try again. These 2 points. Here we go. That looks better. Okay. So the slope of the line that connects these 2 points is called the average rate of change, right? The slope of the secant line, we also call this AROC for short. Okay. So if I have these 2 points here at A and B, right, how would I actually go about calculating the slope? Well, I would just use the good old slope formula. And so I'm going to do that in a little bit, but here's the main thing we're talking about today. So from A to B, there are a couple of things that are true about the function f of x. It is continuous, and it is differentiable throughout this interval. Continuity, differentiability are the 2 key factors here. So here's what the mean value theorem says. If you pick an interval for this function where it's continuous and differentiable, then what it says is there is at least 1 point in between this interval from A to B. 1 point for sure, called C. And C for us is going to be somewhere around there. And at this point C, if I were to draw the tangent to the curve at C, the tangent line to f of x at C, right? So what do I call this? Tangent line to the curve, slope of the tangent line, right? But we also call this instantaneous rate of change, okay? There is at least 1 point C in this interval from A to B such that the slope of those 2 lines is exactly the same. The slope of the secant line is the same as the slope of the tangent line. Or in other words, the average rate of change is the same as the instantaneous rate of change. That's what the mean value theorem says. So let's talk about this. Okay, a couple of things written off to the side here. Okay, in blue, average rate of change. What else do we call that? AROC for short. Right? What else do we call that? Slope of the secant line, right? How do we calculate the slope? Well, we use our handy-dandy slope formula, right? y2 minus y1 over x2 minus x1. F of b minus f of a over b minus a. What mean value theorem says is that all of these things are equal. There is some point C in between A and B where the average rate of change is going to be the same as my instantaneous rate of change. That there's some point C where the AROC is going to equal the IROC, where the slope of my secant line is going to equal the slope of my tangent line, where f of b minus f of a over b minus a is going to equal, how do I calculate slope of a tangent line? Right? I'm going to take the derivative of f and I'm going to plug in c. Okay, So this is 4 ways of kind of stating the same idea here. And the reason why I'm showing you so many ways of talking about this idea is because these are all the ways a mean value theorem question could be asked. Now, typically what you're going to be asked when you get a mean value theorem question is, what is the C value, right? What is the value in between A and B that makes all of this equal to each other? Okay, but it may not always say that, right? It may say find the x-coordinate that makes the slope of the secant line equal to the slope of the tangent line, or find the x-coordinate where the average rate of change is equal to the instantaneous rate of change. Or it could say find the x-coordinate that makes the mean value theorem hold true. Okay, and in all of those ways of asking this question, typically what you're solving for is this C value, right? What is the C value in the interval from A to B? Now, if we look back at this graph real quick, we actually can see there's another potential C value. So I'm going to call that C1, right? Because somewhere at about 1.5 is another C value where if I draw a tangent line here, right, it looks to have about the same slope as my blue secant line. So you may have more than one x-coordinate that makes the mean value theorem hold true. Okay, so let's write a couple things down here. First of all, we have the formal definition of the mean value theorem. If y equals f of x is continuous at every point of the closed interval from A to B and differentiable at every point of its interior A to B. So kind of like when we talked about increasing and decreasing functions, right? Differentiability doesn't have to be true at the endpoints. The main thing here is that we have a closed interval. In that interval, we have to have continuity, we have to have differentiability, and then we can say there is at least one point C in that interval. And one thing I want you to take important note of here is that C cannot be one of the endpoints. It has to be in the interval. There is at least one point C in the interval that makes this equation hold true, that f prime of C is equal to f of B minus f of A over B minus A. Right, that the average rate of change is equal to the instantaneous rate of change at some value. Okay, let's look at some more graphs. So let's take a look at this first one. This one looks like an absolute value graph, and I have 2 points picked here. And so what I'm going to do is I'm going to draw my secant line that connects those points, and I purposely picked these 2 points so that the slope of that line is going to be 0. So now if I look at the graph between those 2 points, is there any place where the tangent line would have a slope of 0? Now some of you would say, how about at x equals 0, right? If I draw a tangent line here, isn't that a slope of 0? Wrong. That is actually a corner. Remember, at a corner, the derivative does not exist, right? We have a different slope from the left and the right. So we have a corner here. That means that my function is not differentiable at every point in the interior of my interval. And so that means the mean value theorem, MVT for short, is going to fail over this interval. Now, it's not a guarantee, right? But that is the reason why, right? Because we don't have a place in between these 2 points that has a slope of 0, right? The most likely place should have been here at x equals 0, but there is no tangent line there, right? Because it's not differentiable there. Okay, let's take a look at another graph. How about the step function? So I have 2 points picked here at 1, 1 and 2, 2. Draw my tangent line that connects those, and that line has a nice easy slope of up 1 over 1, right? But in between those 2 points, so again, this is from x equals 1 to x equals 2. Is there any point in the middle there that has a tangent line with a slope of 1? Nope, right? And so that's because it's discontinuous discontinuous. And again, the mean value theorem fails over this interval, okay? Now, just because a function has a corner somewhere, right, a non-differentiable point, doesn't have to be a corner, or it has some sort of discontinuity, right, doesn't mean that the mean value theorem is going to fail always, right? We just have to pick a domain where it wouldn't fail, right? So, we can look at both of these graphs and pick a different domain. I'm purposely picking domains that are going to make the mean value theorem fail, okay? So it's all about what's happening in the particular interval that you're choosing to focus on, okay? So let's look at a mean value theorem question. So example 1 down here says find each value of c in the interval from 0 to 2 that satisfies, and now you have to recognize this as the formula for the mean value theorem for the function y equals x squared. Okay, so ultimately we're trying to make the AROC equal to the IROC, the average rate of change equal to the instantaneous rate of change. And the way I like to go about this is I just like to do each of them separately, and then I'll make them equal at the end. So AROC, right? This interval is from 0 to 2, right? Y equals x squared is a polynomial. This is continuous everywhere. It's differentiable everywhere. Don't have to worry about any of those. So let's calculate. So I'm going to do f of 2 minus f of 0 over 2 minus 0. And these should be some easy calculations because this is a nice little polynomial we got here, just x squared. So we get 4 minus 0 over 2, which gives me 4 over 2. And so the average rate of change is 2. Okay, now let's calculate the instantaneous rate of change over the same interval. And so, instantaneous rate of change, we need a derivative. So first thing I like to do with is I like to start with what is the derivative function, right? So don't worry about mean value theorem here. You have to get your derivatives right. Y equals x squared, luckily for us, that's an easy derivative. That's just going to be 2x. And now I want the derivative at a specific x value, which I will call c. So plug c into my derivative, I will get 2c. And now what I'm going to do here is I'm going to take my average rate of change, which was 2, my instantaneous rate of change, which was 2c, and now I'm just going to set these things equal to each other. And so I want to know, where does 2 equal 2c? And so lucky for us, this is an easy calculation. Divide both sides by 2, and I get that c is equal to 1. And now this is my final answer, but you do want to make sure that whatever c value or c values, if you get multiple answers down at the bottom, right, falls within the given interval, right? Anything that's an endpoint of this interval would not be counted as an answer. Anything that's outside the interval would not be counted as an answer. C is equal to 1, right? That is my only answer here, right? That is the only x coordinate that is going to satisfy the mean value theorem. So ultimately, not that much work that has to be done here, right? Calculate your average rate of change, calculate your instantaneous rate of change. You're solving for c, which is that x coordinate that makes those two things equal to each other. Okay, let's do one more of these. Example 2. This one, slightly more complicated function. Let f of x equal root 1 minus x squared over the interval bracket -1 to 1. Find a tangent to f that is parallel to the secant created by the points -1 comma f of -1 and 1 comma f of 1. So the wording here is a little bit confusing, okay? Find a tangent to f that is parallel. Well, the word parallel should be familiar to us, right? So parallel meaning that the slopes are equal. Okay, so I want to find a tangent to f that is parallel to the secant, right? So I want the slopes to be equal, so that tells me I'm doing mean value theorem. Okay, here we go. So they gave us the 2 points here, right? But really all we need is the interval, right? -1 to 1. Okay, so we're going to do f of 1 minus f of -1 over 1 minus -1. So f of 1, plug 1 into the function. 1 minus 1 squared is going to be 1 minus 1, which is 0. Root 0 is 0. Minus, take -1, plug it into the function. We're going to get the same thing. We're going to get 0 all over 1 minus -1, which is 2. And so we get 0 over 2, which is 0. Okay, so the average rate of change here is 0. So what we're kind of looking at here is something similar to one of those graphs from up above, right? Average rate of change is 0, right? So we're kind of looking at 2 points here that are on the same y-coordinate, kind of like this absolute value graph from earlier. Hopefully we won't have any corners on this one. Okay, so instantaneous rate of change. Got to start off with my derivative, and on this one, right, root 1 minus x squared, I'm actually going to rewrite this real quick as f of x equals 1 minus x squared to the 1/2 power. Okay, and I think I'm going to change this up here a little bit. Let's get rid of that. Okay, and so now I'm going to start off with some power rules. So 1/2 the quantity 1 minus x squared to the -1/2, and then I'm going to multiply by the derivative of the inside, which is -2x. I think we've seen this derivative before. And so what are we going to get here? This is going to be negative x, because the 2 and the 1/2 will cancel, over, and now 1 minus x squared to the -1/2 means root 1 minus x squared in my denominator. So there's my derivative. Okay, so now that's my derivative function. I want the derivative at some x value that I don't know. I will call that x value c. So I'm just going to plug c into my function here, and I'm going to get negative c over root 1 minus c squared. So there's my instantaneous rate of change. At c, average rate of change is 0, right? And so let's set these equal to each other. So we're going to get negative c over root 1 minus c squared, which is going to equal 0. So I have a fraction that I'm trying to make equal to 0, so I can just make the numerator equal to 0. And so that means that c is going to be 0. And so that is the x-coordinate that satisfies the mean value theorem here. Now, this question kind of specifically said, find a tangent to f. So what I'm actually looking for on this one that makes this question a little bit different is, what is the equation of the tangent line going to be at this x-coordinate? So here's the thing, right? I already know the slope has to be 0, right? So I'm just going to take this x-coordinate, plug it back into the original function to get the point there, and now I can get the whole tangent line. So f of 0 root 1 minus 0 squared is going to be 1, and so the tangent that is parallel to the secant from -1 to 1, right? I'm going to write this out in point slope form, is y minus 1 equals the slope. Again, the slope of this, this tangent line is going to be the same as the slope of my secant, which was 0. So I'm going to get y minus 1 equals 0 times x minus my x-coordinate, which was 0. And this is my actual final answer for this question. Okay, now we can simplify this. We can rewrite this whole thing as y equals 1, right, which is also totally acceptable. Okay, so we're going to stop here for today. That is it for the mean value theorem. Okay, most of the time we're not going to be finding the equation of the tangent line. We're just going to focus on the finding the x coordinate where the mean value theorem is going to be true, right? So find the average rate of change, find the instantaneous rate of change, set those things equal to each other, and solve for x. And that will call it a day for us. So I will see you next time.